Okay, now I am recording, and I want to go over what we have done so far. So first, we have calculated airflows. Quite easy because we just multiply 20 CFM times the number of people. And the only thing is that we have to do this either with the whole building or room by room. If we are working in a TDS building, in a TDS center, for example, we have to do this room by room. We don't calculate the total airflow of the building because each room, it's like a system itself. Okay, so we have different, we have the computer lab, we have the classrooms, we have the lab, we have the lobby. So all these spaces are a problem itself. So we have to calculate airflows individually in each room. Um, if we have a residential building, if we have a single family house, if we can calculate the total airflow of the house. But if we have a building with different uses or with different schedules or with different occupancies, then each room, we have to calculate each room separately. So this is the first thing we have done. Okay, so how many people do we have here? What is the use of the building? If it's not a smoking area, or it's not a theater, or it's not a gym, we can just multiply the number of people times 20, and we have the total CFM. So this is how we calculate the airflow. And then we have to dimension the ducts. So we have to select the right dimension of the duct, the diameter, if we're working with a round duct, or the two sides, the width and the height. If we are working with rectangular ducts. And then we have to check that the velocity of the air is within limits. So we have like 1,000 or 1,300 feet per minute when the duct is close to the air handling unit, and we go down until, let's say, 200 feet per minute when the duct is close to the diffusers. Okay, so keeping those numbers in mind, it's fine. Then we have calculated the heating and the cooling loads for the air handling unit. Okay, so we are assuming there are other ways to do this, but since we need air handling units, we are working in large buildings, in public buildings or commercial buildings, we need air handling units. So I have decided that this year we are going to connect everything to air handling units. So we are calculating the heating coil and the cooling coil. So we are calculating the heating and cooling loads. Okay, so depending on the airflow, we can calculate the heating and the cooling loads that we need in this air handling unit. And finally, what have we done? We have connected this heating coil and this cooling coil to different devices to produce the energy. So we can have a boiler, it can be a gas boiler, so we can burn any fuel. We can do that, but at least if we are burning fuel, make sure that we are burning gas, which is the less contaminant of all the fuels that we can burn in our buildings. And if we are using condensing boilers, it's much better than using non-condensing boilers. Okay. Then we can use pellets boiler. Pellets boilers are good, or because they are using renewable energy. So fossil fuels are not renewable. But wood, everything that is related with wood, it's renewable. So if we burn wood, we make sure that at least we are not running out of natural resources, as long as we plant at least as many trees as we cut down. And this is, we don't have to worry about that, because the rules and regulations, at least in the United States, in the European Union, for every tree that you cut down, you have to plant 5, something like that. Okay, so they make sure that if you are working with wood, so you don't run out of wood. Maybe there was a time in which people were just cutting down forests. It happened in New England, in the United States, in the 18th or 19th century, because the industry was booming. But in the 20th century, that changed, and in in at least in the United States, in the European Union, working with trees, it's something serious. There are other areas in the world in which probably they are not taking much care about this. Anyway, wood, it's a renewable energy, period. Uh, I'm not sure, well, I'm not sure. Um, I'm not happy what they considered about the CO2 emissions, because by burning wood, we are emitting a lot of CO2 to the atmosphere, but they consider the cycle, okay? Because when the tree grows, it absorbs a lot of CO2, and then yes, when we are burning that tree, we release probably less CO2 that they have, that the trees have absorbed during their lives. So if we analyze what we are emitting when we are burning wood, we are emitting CO2, and it's that good? No, because but if we consider the balance, the whole life cycle of that tree, it absorbs much more CO2 than it emits when it's burnt. It doesn't happen, well, it doesn't happen with fossil fuels. Fossil fuels uh, come from living beings. I mean, there were animals, plants that after millions of years under certain conditions of temperature and pressure, they became fossil fuels. So I'm sure that they absorbed a lot of CO2 during their lives, but it happened millions of years ago. Okay, so controlling the balance of a tree, it's easier than controlling balances of the what now we call fossil fuels. Anyway, um, we have boilers. If you have to use boilers, make sure that we are using gas condensing boilers. They are the most efficient and the less contaminant. We can use pellets boilers. Okay, that's an option. It's considered renewable energy. And when it comes to CO2 emissions, if we consider the balance or the whole life cycle of the tree, it's positive. Or we can use electric devices. So we can use chillers or heat pumps. And today I'm going to go over this because what kind of chiller or what kind of heat pump do we want to use? Well, it depends. I have included here this cooling tower because if we are using this water-cooled chiller, we need cooling towers. Probably I should include here, let's say, air cooled.
Fernando,
Yes.
I'm here.
Oh, great. I I missed you.
Yay.
Okay, great. Um, air cooled chiller. This one. Okay, so I want to include here this air cooled chiller. And we can include a ground source heat pump. Which is it's difficult finding a ground source heat pump, something like that. Okay, so this is the catalog of the devices that we have used here. Are there more? Uh, well, when it comes to energy producers, I think 99% of buildings will use one of those, or we can combine those devices, because I think we have boilers, fossil fuel boilers, can be gas, oil, whatever. We have pellets boilers, water-cooled chillers, air-cooled chillers, heat pumps, and cooling towers. So I think if we have this, I think we can cover most of the buildings that we're going to design. But now, what is the next step? So, okay, so we have calculated the airflow and we have dimensioned the ducts. We have calculated the heating coil and the cooling coil. We are heating loads and cooling loads. And finally, we have selected the devices, the energy producers, and then we have connected these energy producers to the air handling unit. So this is what we have done with the schematic drawings, and we have done this with a Revit file. But now we have to speak about the energy efficiency or the efficiency of those elements, okay? And that's important because it's not just selecting a device. We have to select the right device. And it's not, okay, so what is the best one? Is it a water-cooled or an air-cooled chiller or a ground source heat pump? What is better or what is worse? Okay, there are different factors. We know that we have to place these on the top of the building, on the roof of the building. We have to place these on the basement. This is an indoor device. This is an outdoor device. So there are some constraints. If we don't have enough roof area, can we use those devices? Probably not. And then we have to use these ones. If we are using a ground source heat pump, we know that we need to dig a lot of boreholes, and this is quite expensive. Okay, so those are constraints, space, budget. But if we don't have any constraint, we should be able to select the most efficient one. So what is the most efficient one? There is not an answer to that question. If there were an answer, everybody would use the same device, and we can combine those devices in different buildings. So we have to study what we want. We have to study our problem, and then after analyzing pros and cons, then we can make a decision. But other than telling you that do not use a coal boiler, that's the only thing that we shouldn't use, because coal is the most contaminant fuel that we can burn. The second is oil, so oil boilers, it's the second worst option that we can have. Gas boilers, if they are condensing gas boilers, they are quite good when it comes to emissions. And heat pumps or chillers work or run on electricity. So if something runs on electricity, we don't have CO2 emissions on site where our building is. But where does the energy that we are using come from? This is what we have to ask ourselves, and this is what we are going to talk about today. Okay, so if we are using, this is the energy efficiency for heat pumps. Okay, so we are not talking about this concept for boilers or either a pellet boilers or a gas boiler. We're not talking about these two concepts. But when we are talking about heat pumps that run on electricity, we need to become familiar with this. So the first concept is the COP. This is coefficient of performance. So COP stands for coefficient of performance. And EER stands for energy efficiency ratio. Okay, so they are talking about the same thing. So we have the COP or the EER. It's a way to classify the efficiency, the energy efficiency of a heat pump that runs on electricity. Describe the heating and cooling efficiency of air conditioners. They indicate the ratio of heating or cooling provided by relative to the amount of electricity. Okay, so what does it mean? So we analyze the heating or cooling load that this device is providing, divided by the amount of electrical input required to generate it. Okay, so it's okay, so both concepts COP and EER is the thermal energy divided by what they call it here, electrical input. Okay, so that's important because this is the thermal energy that we're using. This is our heating or cooling load. Okay, so this is what we have calculated so far. But now we need to calculate the electrical input because for the second principle of thermodynamics, we know that we can't, well, a heat pump needs electrical input, it needs electricity to run. And by running on electricity, they can generate thermal energy. And the ratio between the thermal energy that we receive at home or in our buildings and the electrical energy that we need to run the heat pump, this is the concept of the COP or the EER. Okay, and this is very important. And then what's the difference between COP or EER? Well, some people, you will hear that COP is for heating and EER is for cooling. I wouldn't say that. I would say that COP so we can make it smaller. As it's stated here, COP it's unitless. It's a-dimensional, so we don't have units for the COP. Why? Because we are comparing, let's say, watts and watts. Why are we comparing watts and watts? Because the electrical input, it's always in watts. So when we're talking about electricity, we're not talking about BTUs or, no, we're always talking about watts. So if we generate thermal energy with international units, we are talking about power, which is watts, okay? So this is the COP. What is the EER? It's the same, it's thermal energy, but this thermal energy, it's in BTUs. And the electrical input, it's in watts. Why are we doing this? Well, because we have, there are countries that are using BTUs, and for them, it's very, well, it's difficult to turn BTUs into watts. So there are a lot of manufacturers, there are a lot of providers, and there are a lot of people installing these kind of things, and they are used to BTUs. And now if we changed, it would be a mess because they would have to, well, eventually it will happen. But so far we have these two concepts. I'm familiar with the COP because in the European Union, we are using watts for thermal loads and we are using watts for electricity. In the United States, well, we are using BTUs for thermal energy and we are using watts for electricity. So that's why we have this. Okay. Anyway, it's always the same. So both concepts are the same. It's a relationship between the thermal energy that we are generating with our device and the electrical input, the electricity that we are consuming to generate this thermal energy. Okay, so if we look at this, here there is a very simple example. So if an air conditioner generates 5 kilowatts of heat from a 1 kilowatt electrical input, the COP is Okay, so that's something that we have to keep in mind. There is no limit for the COP, and the higher the better. And there is no limit for the EER, it's the same. So the more the energy we can generate, the more the thermal energy we can generate with the same electrical input, the better. Okay, so they are the engineers, mechanical engineers, they are working with to improve or to increase the COP or improve the EER of those heat pumps. And they are doing this by manufacturing better compressors and expansion valves, and they are working with the gas or the fluid that it's running through the compressor and the expansion valve. Okay, do we have anything to say about this? Now, as architects, we are not working with that, so we are just analyzing the COP, and the COP, the higher the better. So there is no, it depends, because no, it doesn't depend on anything. The higher the better. So we need a reference for the COP, and we need a reference for the EER. And this is the most important thing. So what are common COPs? Okay, so for let's say air to air systems, the COP ranges from, let's say, let's be optimistic, from 2 to 3. Okay, for air to water, and yeah, let's say from 2.5 to 4 water. And for ground source heat pumps, common values are from, let's say, 3.5 to 6. Okay. So if we can decide ground source heat pumps, it's better because the COP is the highest. If we, of all the heat pumps that we have available in the market, ground source heat pumps are the most efficient. What if we have a 3.5 ground source heat pump and we have a 4 air to water heat pump? Okay, so this is better than this. Yep, but usually when we have only a 3.5 ground source heat pump, it's because of the outdoor conditions. So under these conditions, we won't have a 4 air to water, we will have a 2.5 air to water. So ground source heat pumps are always better than others. What is the problem? The problem is the boreholes or the drill, or the holes that we have to drill. That makes the system very expensive because we have to drill holes, and this is expensive. I don't know why, but it's quite expensive. With these air-to-air systems or the air-to-water, let's say air-to-air or air-to-water, we don't have anything, so it's much cheaper because we don't need to dig those holes. So that's it. So this is the common COP values. What are EER values? I have to find out because I'm not familiar with the values of heat pumps. Okay, this is COP. and this is the EER, the EER. Yeah, I think those values, they are higher. Okay, so yeah, the ER values range from 10 to 20. Okay, so again, the air-to-air EER value would be lower, and the ground source heat pump EER value would be higher. Okay, but those common values are from 10 to 20. So 10 is something similar to 2, and 20 would be something similar to 6, kind of. Okay. Um, I don't know. I prefer using COP because we are comparing apples and apples. We are comparing the same units with other. Here we are comparing two different units. And why are we doing this? Anyway, those are common values for. But you have to become familiar with both concepts, because if we look at the catalog, if we want to compare two different heat pumps, okay, what is the COP of this heat pump and what is the COP of that one? And then we have to compare. And what is the ER value? Well, it's the rule of thumb, the higher the better. That's it. But if someone is claiming that an air-to-air heat pump has a COP above 6, I wouldn't believe that. Okay. So that's why becoming familiar with these numbers, I think it's a good thing, because they are not cheating, or they are not deceiving you with the qualities of the air-to-air or air-to-water heat pumps. Probably when we're dealing with providers, of course, they are all claiming that their system is the best. And probably they are right. I don't mean that they are lying. They are right, but we have to ask under what conditions. Because under specific conditions, an air-to-air air system can be better than a ground source heat pump. If we are working in a warm country with very mild winters, if the outdoor temperature is not very low, probably an air-to-air heat pump, it's a better choice than the ground source heat pump. But if it's too cold, there is no way. So air-to-air heat pumps are not efficient, are not good enough. So those values that I'm providing you with are values for cold climates. If we are talking about warm climates, it might be different, okay? But for cold climates, I think those are the right values. So now, first decision, do we want to burn something, or do we want to go for electricity? This is the first decision, and it's a huge decision, because burning things, it's much easier. Okay, so the only thing we need is to get rid of the gases that we are producing. But we have a chimney. Okay, we are releasing CO2, we are releasing other greenhouse gases. But when it comes to the complexity of the system, burning things, it's always easier. So that's why people have been burning things since they got out of the cave until the 19th century, or the no mid 20th century. They have been burning things because it's easy. You burn something, you get warmer. You get warm. Perfect. Using electricity, it's much more complicated. It's cleaner, but well, it's the system. It's more complicated. The good thing of the electricity is that we can use electricity to generate a cooling system. We cannot burn something to cool down a space. Okay, so usually boilers are better for heating systems, and heat pumps are not as good as boilers for heating systems in terms of efficiency. But on the other hand, we are releasing CO2 and other greenhouse gases with boilers, and we are not releasing this with the electric system. You know that the TDS center, which is an example of good building, of a highly efficient building, um, it runs on electricity, so we don't burn anything on in the TDS building. There is no boiler, no gas boilers, no fuels, not even pellets. It runs on electricity. Is it good? Well, it's good because we are not generating any greenhouse emissions in our building. The problem is, where does the electricity come from? This is what we are going to study now. Okay, but the first concept, COP and EER. Mm, we are talking about heat pumps. Okay, so we are not talking about these coefficients for boilers. It's only for heat pumps. The higher, the better. The difference, COP is unitless, EER, the units are imperial units divided by international units. And we always use international units, kilowatt hours or kilowatts or watts or whatever, for electricity. What else? Well, we have this concept. I'm going to introduce this concept today, but over the next few weeks, we will analyze this. This is the final energy consumption. So the final energy consumption is the total energy consumed by the users, households, industry, and agriculture. Okay, so we are end users. We don't include here the energy that is lost by delivering. So we can generate the energy somewhere, and then we have to transport and deliver that energy. And they are losses. So we are not considering those losses. And we are not considering the transformation. What is transformation? Well, when we are burning something to generate electricity, this is transformation. We are transforming energy. We're transforming the energy that is embedded in the fuel into thermal energy or into electricity or whatever. Okay, so we don't include that. So the final energy is the energy that we actually consume in our buildings. Okay, we are not working with agriculture or industry, so we are working with buildings. Okay, so this is the final energy that we are consuming in our buildings. It can be electricity, or if we have a boiler, we can burn a fuel and then we can generate that energy. Okay, so all this is final energy. So it's the energy that if we have an energy meter in our building, this is the final energy. This is the concept of final energy. The problem, this is not the total amount of energy that we are consuming, because if we want to bring this final energy from a plant somewhere, we are losing a lot of energy through transportation and delivery, and through transformation. Okay, so there's a relationship between the final energy and the total energy. In architecture, we can work with this concept of the final energy, but it doesn't mean that it's the total energy that we are consuming. Okay, so you have calculated heating and cooling loads. This is the final energy. But now we have to consider where the energy comes from. And this is what we're going to do now. So okay, so the energy is not for free. It doesn't grow on trees or, no. We need to generate that energy, and then we have to transport it. So these are basically 4 different means of producing, let's say, electricity. Let's talk about electricity now. So we have thermal plants. So in these thermal plants, we are burning fuel, gas, oil, whatever, and we are producing electricity. And then we have to transport this. We have nuclear plants. Okay, so by using nuclear plants, we are not burning anything. So I told you many times that this is not harmful, this white gas or smoke that it's going out from this. This is a cooling tower, by the way. It's a huge cooling tower. So it comes from nuclear plants are always close to rivers or lakes or close to the sea because they need a lot of water to cool down the reactor, the core of the nuclear plant. And then we use water, we cool down this, we heat up water, and the water turns to vapor, and we have to release that vapor here. Okay, so this is a nuclear plant. So that's why all these nuclear plants are close to a river, lakes, the sea, whatever, because we need a lot of water to cool down the core of the nuclear plant. The smoke that is released through these chimneys, well, this is by burning coal, gas, fuel. If we burn hot gas, it's not as harmful as if we burn coal or uh, other fuel. But anyway, we are releasing a lot of CO2 and greenhouse gases to the atmosphere. Well, those are this is not renewable energy. Nuclear, it's a non-renewable, but it's considered as a clean energy because we are not releasing any CO2 to the atmosphere. So it's clean, but not renewable. We have an issue with the nuclear waste. What do we do with it? I don't know, mankind has not solved that issue yet, but what we are releasing, it's not harmful. Then we have hydroelectric power. This is renewable. Okay, so because we are using a reservoir, so we're using water. So when the water reaches that point, we release this. We have a dam for sure, and then we move a turbine, and then it generates electricity. So is it renewable? It is renewable because we are working with water. Is it clean? It's clean because we are not releasing any CO2. We're just generating electricity and we are not burning any fuel. So it's a clean and renewable energy. Nuclear, it's clean and non-renewable. Thermal, it's neither clean nor renewable. But it has it has an impact. So building those dams, it has an environmental impact because we are modifying the landscape, and it's brutal. I always show a picture in Spain. Es la presa de Alcántara. Okay, so this is interesting because this is a Roman bridge to go from Spain to Portugal. Very nice place. This bridge has like 2,000 years old or more. I don't know. Yeah, thousands years. And this is the Tagus River. And look at this. So it's a beautiful landscape. When we were kids, we all went to see this bridge because it's something outstanding. It's something that comes from Roman times, and it's still there. Okay? But they decided to build this dam. Okay, this is not from the Roman times, and of course, as you can see, it has a lot of impact. Okay, so you have to use a lot of concrete, and it has an environmental impact building dams. Once it's there, it's renewable energy because you just have to accumulate water here, release the water, and you generate. There's an energy hydraulic plant here, so you generate a renewable and clean energy, but it has an environmental impact. Do we want this? Well, I don't know. It's an option. So if it's there, we use it. But building these kind of dams now, it's controversial as well. Anyway, it's a clean and renewable energy, this hydroelectric power. And then we have the solar. We can have solar or we can have wind turbines. Okay, so this is clearly renewable. But again, we can have solar plants somewhere, and then we have to transport this energy, this electricity, to the house or the city or the neighborhood or whatever. So it's always the same. We generate electricity somewhere, and then we have to transport and deliver that electricity. If we are talking about solar, we can have like huge PV solar plants. Okay, so thousands of PV panels, and now we are generating this. Or we can have this concentration solar plants like this. Okay, so we have thousands of mirrors, and they are all reflecting the sun energy to that specific point. So we heat up this, so we generate a lot of heat here, and that heat uh, generates water vapor, and that water vapor at a lot of pressure, it moves another turbine. Okay, so there are um, different ways to generate or to deal with solar energy. So this is concentration solar plants, and the other one are photovoltaic solar plants. It has an impact. So for sure, it has an environmental impact. This is clean, renewable energy, but you need a huge area to install or deploy all these elements. Okay. Anyway, we can have a solar plant here. We have energy from the sun. It's free, it's clean, renewable, it's perfect. But it has an impact, especially in the landscape. And then we have to transport this here. Okay, so this is the traditional way of looking at energy. And well, we have generation and distribution. So here we have the electric power generation, can be thermal, hydroelectric, renewable, solar, wind, whatever. We need transmission lines, and we have high tension here. When we have these towers, the tension at which the electricity is going or it's traveling, it's very high. And as we are getting close to a city or a neighborhood or whatever, we have to reduce the tension. Okay, and we will talk about this when we are talking about electrical systems. But we have transformers. So those transformers reduce the tension because this is dangerous. Okay, so having this tension within a city would be dangerous. So we have to reduce the voltage, and then we can use that. And well, if we look at this, here we have a residential neighborhood, and here we have the downtown. There's a difference. Here we have tiny houses, but we have a lot of roof area. Okay, so the amount of roof area that we have in residential neighborhoods, it's much bigger than the roof area that we have in the downtown with skyscrapers. So we can change the way we have done this for, let's say, 100 years. Usually we had the production plant somewhere out of the city, and then we needed the transportation, and then we needed the distribution and delivery. But looking at this, if we have residential areas, we can change the way we're dealing with the electricity, and we can have the standalone PV system. With this kind of systems, we don't need energy from plants. We don't need thermal plants, nuclear plants, hydroelectric power, or either, or even these solar plants out of in the middle of nowhere. Okay. So that's a very interesting, and I think in the United States, most of cities or most of people live in this kind of houses. We have a lot of roof area compared to the size of the building, and we have a lot here, and if the lot is big enough, we can make the most of it to increase the amount of PV panels that we have. So I think in the United States, we have the opportunity to change the old-fashioned, the traditional method for energy generation and distribution. Okay, so by making the most of all the roofs that we have here, yeah, we can work with this standalone PV system. Everything comes at a price, so it's not okay. Let's do this. Okay, let's do this, but what do we need? We need inverters, we need batteries, especially we need batteries because if we have sun during the day, if it's cloudy, we don't have any sun. So what if we don't have enough sun to cover all our needs? We need batteries, and batteries are expensive and they are space consuming. Okay, so what is another option? We can have a hybrid system. So we can connect our building to the grid, but we have a system here and we don't need batteries. So if we don't have enough electricity, we are taking that electricity from the grid. And if we have an excess of electricity and we're not using it, we can uh, supply that electricity to the grid. So that would be perfect. If this were a perfect world, that would be the perfect system because if I'm living here in my house over in the evening and because I'm working in the morning, so in the morning I'm generating a lot of electricity and I'm not using it because I'm not there. But what if I can supply this electricity to the grid and then the same amount of electricity that I am supplying, I'm taking in the evening because I'm living there. But now it depends on rules, regulations. So it depends on the country, it depends on the state. If we are just talking about the United States, I don't know, where are we? I think we are here. Uh, Nothing prevents us from designing a standalone PV system. If we are living in the middle of nowhere, in the middle of the forest, and we don't want to talk to anyone, and we don't want to deal with an electric company, so that's an option. But you have to understand that you need batteries, and even if you have a lot of batteries, sometimes you can run out of electricity. If you are okay with that, go ahead. If you want to be sure that you don't run out of electricity, we can go to the hybrid system. So this is what I would recommend. Nowadays, I don't know, maybe in 20 years, things have changed and we can go for this model and we can make sure that we don't run out of electricity. Nowadays, if you are going to decide a single family house, I would go for this. Does it mean that we can get rid of all this? I don't think so, because here in downtown, we don't have enough roof area to provide those skyscrapers with all the energy we need. Okay, so we need to generate electricity somewhere, and then we have to transport and deliver that electricity. But for residential neighborhoods, I think these are good solutions, and we can save a lot of energy. That's why I want to go back to the concept of final energy. So for this final energy, there is always a factor that relates the total energy that we are producing with transformation and delivery. So that makes that means that if we are using this final energy and we are taking this final energy from a nuclear plant or a thermal plant that is 50 miles away from my house, I'm losing a lot of energy. If I'm generating this on site, I'm not losing anything on transportation. Okay, so that's a very efficient way to address this problem. And to have a backup, okay, I can have this. So I can have a supply, I connect my house to the supply grid. And just in case if something works or something terrible happens, I'm sure that I can run all my devices, my heating system, my cooling system, my refrigerator, everything. Okay, so now we are, I think we are here. We are in this hybrid system time in which we can get rid of this. We can get rid of energy plants. We need energy produced somewhere out of the city. But what we don't know. If I could foresee the future, I don't know, but I can't. So will this be the future? Well, I don't know. It seems reasonable because the housing style of the United States. In Europe, very few people are living in neighborhoods like this. People are living here in downtown, and we are all sharing a square meter in different floors. Okay, but in the United States, I think this will work. Anyway, let's see. Um, we are architects. Can we decide on this? We can't. So these are decisions that come from the government or from the, I don't know, but those are decisions that individual architects cannot take or cannot make. Okay, so we cannot decide, okay, let's get rid of thermal plants. We can't say that. So countries, in theory, they are committed to renewable energy. And so there are a lot of conferences or there are a lot of agreements between different nations or different countries about a renewable future. Is this controversial? It is. Why? I don't know. There are a lot of course, if you have made an investment on a thermal plant or in a nuclear plant, and sometimes no, in 10 years, we will get rid of all thermal or nuclear energy. You say, what? So I have spent millions of dollars on building this nuclear plant, and you are telling me that in 10 years I have to lock down? Uh, so there are a lot of interests, there are a lot of politics here, economic issues, but um, countries are committed to this. And I think there's nothing we can do to stop this. We can slow it down. Maybe it's not in 10 years, it will be in 50, okay? Or maybe it's not in 50, but it will be in 100 years. Okay, I don't know. But there is a trend that we have to change our non-renewable production, energy production, and then we have to start replacing this non-renewable energy production by renewable energy production. Again, it's not easy. It doesn't happen overnight, but I think the whole world is moving in that direction. We can slow down things or we can speed up things. Some countries are speeding up, other countries are slowing down, but I think this is the direction in which the world is moving. So here I have some graphics about the European Union and the United States. Why? What about China? Well, I don't know. I'm not familiar with China, and I'm sure that what happens in China matters. But in places where, well, I'm living in the European Union, or I used to live in the European Union, and now in the United States. So what's going on? Uh, okay, so by 2020, there was a commitment for all the European Union countries that by 2020, at least 20% of the energy had to be produced by renewable resources. So by 2016, we were close to the 16.9. Okay, so we are close to 17. What is going on now? Well, I don't know. We are in 2020, so by the end of this year, we can realize whether we have met that goal or not. These statistics, this is very good website, by the way. This is Eurostat. So if you want to know anything about Europe, what the sources of energy, what people, the food, what kind of the habits of people. So everything's here in Eurostat. So we pay a lot of taxes to yeah to give money to these organizations. And this is interesting because here we can see what countries have met. This was in 2018. Okay, so the target is by 2020, but in 2018, so we have this picture. We don't have statistics of, so we need a year to develop those statistics and to look at it and look what has happened. Okay, so that's why the most recent statistics are from 2018. So where are we? Well, this is the European Union, and of course, countries like Sweden, Finland, Denmark, Austria, Portugal. So they have met the conditions for 2020. So in 2018, they had already met this goal of more than 20% of the energy is generated by renewable resources. Great. There are other countries, Spain is getting there. France is, it's always there. Yeah, so they are a nuclear country, so they rely on nuclear plants. So they built a lot of nuclear plants in the 60s and 70s, and they are not for renewable energy. So this is a strategical decision. So they are not thinking of the planet, they are thinking on their own. Probably they are right. But although we have this Paris Agreement that everybody refers to, so in France, they are not meeting those commitments. Okay. And then we have other countries that will, anyway. So in global, we're in the European Union, it's close to meet uh, that goal. Okay, so by 2020, 20% of the energy is coming from renewable resources. What about the United States? Okay, so I have found this. So by 2050, okay, so the goal, it's always, we have this 2050 in the horizon. By 2050, all buildings should be zero energy buildings. By 2050, 100% of the energy in the United States will be renewable. I think it's too optimistic or ambitious. I don't know. So they have this WWS that stands for wind, water, and solar. Okay, so will we have 100% of the energy produced by wind, water, and solar by 2050? I don't know. You'll be there, so you will find out. And what is this? So that's interesting because here we have all the energy that or the all the energy production, the renewable energy production that we can consider. Okay, so we have residential rooftop solar. So they claim that 8% of the total energy of the United States will be produced on site. Okay, so in the house. Okay, that's good, 8%. I think this is doable. It's not optimistic. I think if at least half of the roofs of the United States had these PV panels, I think we can produce more than 8% of the electricity, or the total electricity that the country needs in rooftops. Okay, so I think this is doable. So what about solar plants? 25%. Okay, solar plants, it's well, so these are solar plants, can be solar concentration or can be PV panels. 25%. Well, it depends. I don't know. Well, here we have, I think this, oh, so this is solar plant. This is only for PV because they have this concentrated solar plant. So it's 7.3. Okay, so I think this is PV, photovoltaic panels, and this is the concentrated solar plant. So it's more than 30% solar. Well, I don't know. I think this is too optimistic. Here we have onshore wind and offshore wind. Onshore means that it's inland, and this is offshore. So this is in the middle of the sea. Well, in the middle of the sea. I don't know. I think this is too much. 30%. the onshore wind. It's too much. Anyway, those are, and as you can see, this is the, if you add all these up, 8 plus 25 plus 7 plus 30 plus 17, this is more than half, much more than half. And then we have other, which is, we have wave energy, we have geothermal energy. Geothermal, it's from heat source that we have thousands of feet underground. Hydroelectric, I told you that hydroelectric is not, now it's controversial. So if the country doesn't have a lot of hydroelectric plants, I don't think they are going to build more. And then we have these tidal turbines. So they make the most of the tides. Okay, so when the tide goes up or down, so it generates electricity with these turbines. Okay, so this is the prediction. They always connect this growth, this renewable market growth to jobs. Okay, so this is optimistic as well. So they claim that they can generate more than 5 million jobs with these new plants. Well, among these jobs, some architects, I'm sure, that would be included, because if you want to do this, you have to design buildings, zero energy buildings, to make the most of this rooftop solar energy. Okay, so some of these 5 million jobs, some architects will be included here. So this is the global, well, the global perspective. We are focusing on the European Union and the United States. But again, will it happen in 2050? Well, we don't know. I was not optimistic that this could happen in 2020, this target of 20% of renewable energy in the European Union. But unless they are deceiving us, I think, yeah, they will meet this requirement or this target. Yeah, why not? So will that happen by 2050? We don't know, but the world is moving towards that direction. And I told you, it can be, someone can slow down this process, or someone can speed up the process. If it's not in 2050, it will be in 2060 or in 2070. But I think this is the goal. But what can we do now? Well, so far we have to focus on what we can do. So we have to focus on these devices that we are familiar with. We have to reduce the heating and cooling loads. So there are different ways to reduce heating and cooling loads. This year we are talking about heat recoveries, and we are talking about schedules to adapt the heating and cooling loads to the occupancy. So by doing this, by using this technology of the heat recovery in the air handling unit, and by using schedules, we can reduce the amount of energy that we are using in our building. And second, we haven't done that yet, but we are going to create, or we are going to work on some assignments about using this concept of coefficient of performance. I think we will use this coefficient of performance because it's worldwide, and I think it's more general, and you don't have to worry about units, because I'm sure that if we were using the EER, there would be a lot of mistakes by using BTUs and watts and whatever. Okay, so if we are using the COP, I think it's better. So what's next? So on the next assignment, we will be focusing on electrical devices. So we want to be focusing on pellets boilers or condensing boilers, gas boilers. So we will be using in water-cooled chillers, air-cooled chillers, heat pumps, and we will analyze COP. Okay, so with the heating loads that you have already calculated for this, now we will talk about this concept of final energy, because the final energy consumption is the actual energy that our device, our heat pump, is consuming. Okay, so we have to work with this COP. I will provide you with some catalogs, and I will provide you with some technical documents about different heat pumps, because this COP it's related to the outdoor conditions. Okay, so depending on the outdoor condition, uh, I have given you a range of values here. So 6 is the optimum, and 3.5 is the worst. Why? Because it depends. So the same ground source heat pump can work with a COP of 3.5 or 6, depending on where we are. Okay, so this is what we need to understand now. So I will provide you with these technical documents in which you will see how we can change the COP depending on the outdoor conditions. The same thing that we saw with the enthalpy, that depending on the outdoor conditions, we can change the enthalpy. So depending on the outdoor conditions, we can also change the COP. Okay, so I think we will work with the same Excel file that we are working with. I will add another column with the heat pump COP. And that heat pump COP will be related to especially the outdoor temperature. Okay, so it's not the same outdoor temperature, or it's not the same performance with 0 Fahrenheit or 20 Fahrenheit. Okay, so we will change that COP, and then we will add another column to calculate the final energy that we are consuming. Okay, so we have calculated the energy that we need, but this is not the final energy. If we are using a heat pump, now we need to apply the COP to find the final energy. And finally, we will calculate the CO2 emissions that we are generating by running our system. And it depends on where the electricity comes from. Okay, so if the electricity that we are using comes from a thermal plant, we will generate a lot of CO2. But if the electricity that we are using comes from renewable sources, then the CO2 that we are generating, it can be dropped. Well, so this is what we are going to do over the next couple of weeks. So we are not going to work with Revit over the next 2 weeks. We are going to work again with calculations, and then the last 3 weeks of this course, we will work with Revit again to work with the piping system and the drainage system.